This is section 5.5, which is the application section of graphing, basically graphing. And the first box here, this blue box says simple harmonic motion. And it says if the equation describing the displacement y of an object at time t is y equals a sine omega t or y equals a cosine omega t, then the object is in simple harmonic motion. So first of all, that little w, that is a Greek letter. It's a lowercase symbol for omega. And it's the same thing as k. It's just that when we're talking about application problems, we switch the variable. This happens a lot in a lot of topics. So just try to remember that it's k. So the amplitude is the same. The period is 2 pi over omega, which is the same thing as 2 pi over k. And the frequency is the reciprocal of that. So this is simple harmonic motion. So that means I'm not going to have any phase shifts or anything like that in these first problems. But in the textbook, we do get into problems that have phase shifts and vertical shifts and all that. So these would just be the most basic ones. So let's do the first example here, and I will do a lot of examples for this. No two are the same, and you'll quickly see that. So this is modeling a vibrating spring. So it says a mass is suspended from a spring. The spring is compressed a distance of 4 centimeters and then released. It is observed that the mass returns to the compressed position after 1/3 of a second. Find a function that models the displacement of the mass. And then B is sketch the graph of the displacement of the mass. With these problems, they're always going to say find the function and then sketch the graph. So I need to be really clear about this. You want to sketch the graph before you come up with the equation. The graph is usually just it's going to give you all of the necessary parts that you need, and you don't have to sit there and calculate or guess. So I'm going to actually sketch the graph for all of these first. So let's look at the first sentence. A mass is suspended from a spring. It's compressed a distance of 4 centimeters and then released. So if I were to draw a picture of this, it would look something like this. Let's call that, this is my mass. It's just a block. And, let me move that. So it's a mass, and then there's going to be some kind of spring. That's the worst spring I could draw. And so you have this mass hanging from a spring. And let me move that up to show you what I'm trying to do. So we're trying to put the mass on the x-axis. So it says it's compressed a distance of 4 centimeters and then released. So that means we're taking this spring and we are compressing it 4 centimeters. Okay, so that means we're pushing the spring up 4 centimeters. So if I draw that on the graph, I'm going to call this 4. This is where our mass would start. It would start at 4. So I'm going to read each sentence and then put that on the graph. I'm not going to try to force the graph. So it says it is observed that the mass returns to the compressed position after 1/3 of a second. So after 1/3 of a second, it's going to return to that spot. So in simple harmonic motion, we're not taking into account any realistic physics. So we're just saying this thing is going to compress, go down, and then go back up. So we're creating simple equations. So if you look at that, it starts at its peak and it ends at its peak. So that means halfway between, it's going to hit its lowest point, which is, we're going to assume, is -4. So then I have this graph like this. And so this would be the B part. So we have what looks like a cosine graph. Okay, if you look at that, I've drawn a cosine graph, so now we already have a bunch of parts here. So now let's find the function based on what we drew. We don't need to create more numbers on the axis or anything. Let's do A. So I know I have a cosine graph. The amplitude is 4. There's no vertical shift, there's no phase shift, and the period is found by 2 pi over omega, and we already know the period is 1/3. So if we solve the equation 1/3 equals 2 pi over omega, we would get 6 pi. So omega is 6 pi. So that's our k value. So this would be 6 pi x. Let's use t because we're dealing with time there. So this would be our equation. Y equals 4 cosine 6 pi t. And we've already sketched the graph. The only thing I might add in here is, what's 1/2 of 1/3, so 1/6 in the middle. And that's our first example. Okay, our next example is modeling the brightness of a star. So it says a variable star is one whose brightness alternately increases and decreases. For the variable star delta Cephei, the time between periods of maximum brightness is 5.4 days. The average brightness or magnitude of the star is 4, and its brightness varies by plus or minus 0.35 magnitude. Find a function that models the brightness of delta Cephei as a function of time. Sketch a graph of the brightness of delta Cephei as a function of time. So once again, I'm going to actually start with this B part. Let's work on the graph. This is one that is particularly difficult if you don't draw the graph first. Okay, so I'm going to go back to the paragraph and just read some of these things again. So it says the time periods between maximum brightness is 5.4 days. So that's really just telling you your period almost directly. So we're talking about this sentence. Okay, so what I'll do with that is just say, okay, well, I know the period's 5.4 days. And I know this axis is in days. And then the average brightness, anytime you see that, so if you, it's always going to talk about, that's really your vertical shift. So your vertical value is going to be where the function goes above and below. So that would be your average, and so that's at 4. So I'm going to go to the scale here and put a 4, and I already know that's the midline because that's my average value for a trig function. Okay, it says its brightness varies by plus or minus 0.3 magnitude. So that means it's going to go above by 0.35. And so I'd have 4.35 on the y scale, and then it'll go below by 0.35. So I would have 3.65 as my low number. Okay. It doesn't tell us that it starts at its peak or it starts in the middle. So it doesn't tell you whether it's sine or cosine. So really you could use either. Doesn't give us any specific time at which we're starting the graph. So I'll use cosine again. So I'll have this start at its peak, end at its peak, go to its low point in the middle, draw my function. And there we have our graph. So 5.4 divided by 2 is 2.7, so that's my middle number, and that's about it. So now we can just take all of our information from that graph. So let's do part A. The function that models it. So it's all just sitting there. So we have a cosine function. The amplitude of the cosine function would be 0.35. Has no phase shift. It does have a vertical shift. So I'm going to wait on that though. Let's look at the period. The period is 5.4. So we set that equal to 2 pi over omega. And so omega is 2 pi over 5.4. So I am not going to convert that to a decimal. I'm just going to leave it because it gets messy if we do too much here. So I will go 2 pi over 5.4 t. So that's inside the trig function. And then it has a vertical shift of 4. And that is our function, 0.35 cosine of 2 pi over 5.4 t plus 4. Okay, so these problems are a little more difficult than the ones we just did. Usually I would save these for later, and this would be an assignment. But I really like to emphasize that you need to draw the pictures first, or you should draw them first, because the information sometimes can be hard to get out of the paragraph. So our first one, each day the tide continuously goes in and out, raising and lowering a boat sinusoidally, which just means it's a wave like sine or cosine in the harbor. At low tide, the boat is only 2 feet above the ocean floor, and 6 hours later at peak high tide, the boat is 40 feet above the ocean floor. Write a sine function that describes the boat's distance above the ocean floor as it relates to time. So what I'm going to do first is say the axis here. Now this is t, and I'm going to have the axis represent the ocean floor. And it does tell me directly it's a sine function, so I'm just going to put sine down here, so I know where to start with that. Okay, let's read this sentence. We're just going to go sentence by sentence and put this information on the graph. And it won't make sense until we're done, and we'll just connect the dots basically. It says at low tide, the boat is only 2 feet above the ocean floor. So I'm going to go to the graph and say at 2 feet, or at 0, time equals 0, I'm 2 feet above the ocean floor. Then it says at 6 hours later, at peak high tide, the boat is 40 feet above the ocean floor. So let's put that here. So 6 hours later, it's at its peak. Okay, so that was that second sentence. Not the second sentence, but the second sentence that we read. And that's all it gives us. So we need to figure out what's going on here. So if I look at that graph, there's actually plenty of information here to come up with the function, even though it doesn't look like it. So I just have 2 points on this thing. This is the low and the high. So if I look at that, that tells me that there's got to be a phase shift, or this is a cosine, upside down cosine. So let's say this. 6 hours later, it was at 40 feet. So I'm going to put I didn't put this number here. So on the y-axis, I will have 40. So that we have the peak and the dip. So what we'll do next is create the midline. So the midline's between those two numbers. And 40, how we're going to get that midline number is just subtract 2 from 40. So 40 minus 2 is 38. And then divide that by 2. So this number would be 19. Okay. And that means that the midline is the vertical shift is 19. So I have something finally. The amplitude is the distance between the midline and the high and the low point. So 40 minus 19 is 21. So 21 is our amplitude. Okay, let's see here, what's easiest? Let's do this. I'm going to put another dot right here. And that's a little confusing looking, but so each, from the low to the high, that represents half of your period. So from the low to the high is 6, so that means the whole period is 12. So if this is from the low to the high is 6, then that means there would be a point here at 9. And that would make this one 3. This is 0 on the graph, and then we would have another point back here. Continue this red line. And that point would be at -3. So if you look at what we drew here, we have that is a sine function, and I didn't have to choose this one, so you're going to vary which one you choose. That's the one I chose. So what that represents is a negative sine function, and the amplitude is 21. So it would be negative 21 sine. And there is a phase shift of negative 3. And so then the only thing I have to do is figure out the omega value. So omega is going to be the period equal to 2 pi over omega. So omega is 2 pi over 12 or pi over 6. So this will be negative 21 sine of pi over 6 and then parentheses x plus 3 outside parentheses 19. So that would be my function for that. Okay, so this one is particularly difficult when I usually do this in person. So a team of biologists have discovered a new creature in the rainforest. They note the temperature of the animal appears to vary sinusoidally over time. A maximum temperature of 125 occurs 15 minutes after they start their examination. A minimum temperature of 99 occurs 28 minutes later. Write a function that describes the temperature of the animal as a function of time. So this one doesn't tell you to write a sine or a cosine, it just says write a function. So I will again go through each sentence where it gives me information. So the first sentence is a maximum temperature of 125 occurs 15 minutes after they start the examination. Okay, so what I'll do on the scale here is just go to 15. And I'm not going to force anything out of these problems. I'm going to let it all fall where it falls. So 15, I'm going to have, I'm actually scoot that out a little bit just in case. I don't have enough room, so this is 15. So the maximum is going to be at 125 at 15. Next sentence. Now notice I'm just taking the information directly and putting it on the graph. A minimum temperature of 99 occurs 28 minutes later. Okay, so 28 minutes later after 15 is going to be 15 plus 28, which is 43. And that is my minimum. So my low point is at 43, and that gives me a 99. So just like the last one, it gave us our peak and our dip. And so that represents half of our period. And like the last one, that's all we have. So we have to figure this out from here. So let's start with the period first. This, between your low point and your high point, this is half the period. Okay, half the period, so 43 minus 15 is going to be half your period. So if we just say, well, what is that? That's 28. So this is half of the period is 28. So that means your whole period is 56. Let's do our midline before we do anything else. So the midline is, we're going to get that by subtracting 125 minus 99 and then divide it by 2. So 125 minus 99 is 26. So then to get the amplitude, we're going to divide that by 2. So the amplitude is 13. And then we need to get the vertical shift. So to get the value here for the midline, we're just going to add 13 to 99. So this would be at 112. So the vertical shift is at 112. So this number would be 29. So 15 to 43 is 28. Each of these sections then is equal to 14. So 43 plus 14. So 43 plus 14 is 57. And we'll have a point here. And then we would need to put a number 14 back from 15 because each section has to be worth 14. So this would be at 1. That's the part students usually miss. Okay, so I'm going to draw this function. So we have a sine wave, it looks like. So I'm going to write sine down here, fill out the amplitude. So 13 sine. And then we just need to find the omega value and the phase shift. The phase shift is just 1. Omega is going to be 2 pi over omega equals the period. So 2 pi over 56 equals omega. And since that's easy to do, I'll just, omega is pi over 28. So this one would be 13 sine of pi over 28 times x minus 1 plus 1/12. Okay, so this example is, it's kind of like the last one. It's a little difficult if you try to force it. So Mark Twain sat on the deck of a river steamboat. As the paddle wheel turned, a brightly painted yellow dot on the paddle blade moved in such a way that its distance from the water's surface was a sinusoidal function of time. When the watch read 4 seconds, the dot was at its highest point, 16 feet above the water's surface. The wheel's diameter was 18 feet and it completed a revolution every 10 seconds. Write an equation describing the height of the yellow dot as a function of time. So to help visualize this a little more, it's a wheel and this dot is going above the water and then down into the water and above the water. And it's just repeating that. So it doesn't tell you to write a sine or a cosine, so we're just going to write whatever ends up showing up on our graph. So let's go to the information parts of this. It says when the watch read 4 seconds, the dot was at 16 feet above the water's surface. So I'm saying that the x-axis in this case is the water level and t is representing time. And let's just put that dot on the graph. So at 4 seconds, it's at its highest point, which is at 16. It says the wheel's diameter was 18 feet. So if the wheel's diameter is 18 feet, let's say this is 18 feet, and there's some dot on it, that means it's going to go, half of that would represent your amplitude, because it's going to go all the way up to the top and then all the way down to the bottom. So this one, the 18 represents the whole distance from the top value to the low value. So on our graph, we're going to have a value at -2. So 16 to -2, that's a value of 18. So that represents the diameter of the wheel. So at some point, we're going to have a low point at -2. So now we just need to figure out this midline. So that happens halfway between -2 and 16. So that's a distance of 18. So half of that distance is your amplitude. So we have a distance of 9. So on our y-axis, there would be a 7, because -2 plus 9 is 7. And that represents your vertical shift. And that's about it so far. Okay, and then we go to the rest of that sentence where it says it completed a revolution every 10 seconds. So this thing needs to complete a cycle every 10 seconds. So between the peak and the low point of your function, that's half the period. So between from 5 seconds later, it's got to hit its low. So this would be at 9. This middle number is going to be a decimal because from 4 to 9, that's a distance of 5, and we have to divide it by 2. So this would be at 6.5 because we're going to add 2.5 to 4. Okay, and so now we know what the distance is for each of these sections. It's 2.5. So 9 plus 2.5 is 11.5. And 4 minus 2.5 is 1.5. So we're going to have a value here, a value here, a value here. And let's connect that. So this is just a sketch clearly because this is a kind of an ugly graph. And so now we have this thing. The period is 10. The phase shift is 1.5. And that part is the part that's easy to force out of it. And the equation is just 9 sine. Oh, we have to do the omega value. So it would be 10 equals 2 pi over omega. So omega equals pi over 5. And then x minus 1.5 plus 7. So 9 sine of pi over 5, parentheses, x minus 1.5 plus 7. Okay, and our last example, and I know this is a lot of examples, but I want you to look at a lot of these so that the homework's easier. So this one is a buoy in the ocean is bobbing up and down in harmonic motion. At time equals 2 seconds, I'll just highlight this as I go. The buoy is at its high point and returns to that high point every 10 seconds. The buoy moves a distance from 3.6 feet from its high point to its low point. And it says you decide what height represents sea level without the waves and continue accordingly. So you can either put this above the axis or below, but I always started on the axis because then my equation's easier. And let's just write the equation here. So at time equals 2 seconds, let's put a 2 here, it's at its high point, and it returns to that high point every 10 seconds. So that tells me that I'm at the high point, and it doesn't tell me the high point directly, but then it says 10 seconds later, it's going to return to its high point. And that means halfway between that, you have your low point. So this is a cosine graph that I'll be drawing. The phase shift I can already see is 2. And then in red highlighting, it says the buoy moves a distance from 3.6 feet from its high point to its low point. Okay, and I'm going to say this is sea level, the axis. Okay, so it moves a distance from 3.6 feet from its high point to its low point. So that means this whole distance from high to low is 3.6. So if that's 3.6, we're going to divide it by 2 to get the value here. This is at 1.8, and this would be at negative 1.8. The midline, the way that I drew this, is going to be the x-axis. And let's connect our function here. Okay, so the amplitude is just 1.8. The period is 10. There is no vertical shift. And then we just fill out the equation, and we still need that omega. So 2 pi over omega equals 10, which is the period. So omega is pi over 5 in this one as well. Phase shift is 2, vertical shift is 0. So there is our function.